So let us now kind of review the problems we have. We have an axial problem, we have a torsion problem, and we have a flexure problem. And in each of these problems, once we have chosen either an approximation or an exact representation of their displacement, corresponding displacement fields, we would have the task of determining the corresponding strain fields so that we can exercise the principle of virtual displacements. And the corresponding strain displacement equations for each of these problems are as follows. The first derivative of the axial displacement with respect to the axial coordinate would give us the so-called axial strain, epsilon x. And then we have the first derivative of the twisting angle with respect to the axial coordinate, giving us this quantity called beta. And then for the flexure problem, the second derivative of the transverse deflection field would be necessary for us to carry out the principle of virtual displacements to compute the internal virtual work, as you will see soon. And that differentiation would give us the flexural field. So let's just go over each of these problems to obtain how the corresponding strain fields, epsilon sub x, beta, and kappa sub z, can be obtained from the shape function representations of the right-hand side. So let's focus on the axial problem first. For the axial problem, our shape function generalized coordinate representation was the product or the inner product of these two vectors, the shape function vector and the nodal displacement vector. And if I differentiate the u of x, I would have obtained epsilon x, which means I'd have to take the derivative of the right-hand side of the expression at the top with respect to x, and those derivatives are quite simple, and it would give me this relationship. So in this relationship, we have we will define a new name, which we will use over and over again. We will define this first matrix, the one that is encircled by this green rim, the strain displacement matrix. It's the strain displacement matrix for the axial problem. And of course, u1 and u2 is our vector of nodal kinematic degrees of freedom. In this particular problem, we just have two kinematic degrees of freedom, u1 and u2. But if we had used a quadratic element that contained 3 degrees of freedom, well, of course, the dimensions of both of these matrices may change. For the torsion problem, we need the derivative of the twist field to get this beta quantity, which we will use eventually to compute the internal virtual work. And again, the strain displacement matrix happens to be identical to the axial problem, but the vector of nodal kinematic degrees of freedom are now the twisting angles at the two ends. For the flexure problem, we'd have to take the second derivatives of the cubic Hermite polynomials, for example, and those would be multiplying each of those end kinematic degrees of freedom. And for the cubic Hermite polynomials, if you do the proper two second derivatives, you will obtain these linear polynomials that give us the strain displacement matrix for this problem. And here v1, theta sub z1, v2, and theta sub z2 are the vector of nodal kinematic degrees of freedom for this problem at hand. Now let's just rewrite them all together and also recognize the fact that if we will obviously need the virtual counterparts of the same relationships. And when you look at, for example, the virtual axial strain, the strain displacement matrix is going to be identical to the real field because we'll be using the Galerkin method, right? If we use the Bubnov-Galerkin method, then we are using the same shape functions to interpolate the physical real displacement field as well as the virtual displacement field. So the strain displacement matrices are identical, but the vectors they multiply are the virtual counterparts of the kinematic degrees of freedom. And each of this expression can be written up generically in compact form as follows. The strain, whatever the strain quantity is, equal to a B matrix that multiplies a delta vector. Epsilon could be a vector of strains, or in this particular case, it's not really appropriate to call what we have on the left-hand side strains because curvature is not a strain, but rather a strain resultant of sorts. And on the right-hand side, we would have the B matrix, the strain displacement matrix, and the appropriate vector of nodal kinematic degrees of freedom. And of course, similarly, we would have the virtual counterpart of this particular relationship, where on the left-hand side, we would have the virtual strain resultants, del epsilon, the same strain displacement matrix B on the right-hand side, as well as the virtual vector of nodal kinematic degrees of freedom, del delta. The other ingredient that we would need to exercise the principle of virtual displacements is the constitutive relationships. In this particular case, we have three constitutive relationships to consider. The first one is the one that relates the axial strain to the axial internal force, F sub x. The next one is the one that relates that derivative of the twisting angle, which we called labeled as beta, to the torque, internal torque, which is m sub x, which is the expression shown in the middle. And then the last one is the one that relates to curvature kappa z to the bending moment about the z-axis. And of course, for the flexural problem, we also have a shear force in place, but that is a condensed degree of freedom or condensed internal force, as we have discussed before, and we'll get to it where and how it appears in our relationships. So what I can do now is to combine these relationships and compactly represent them in a matrix vector format. So for that, first I'll define a vector of stress resultants and call that sigma, which contains the axial internal force, the bending moment, and the torque. And then just kind of write this expression where sigma is equal to some c times epsilon, where c is made up of a matrix, in this case a 3x3 matrix, that is made up of the material properties, and epsilon is the vector of strain resultants. So for this particular case of a homogeneous beam, we have this uncoupled constitutive relationships. So the C matrix is only diagonal here, but at this point I'd like to denote the fact that this matrix can be a fully populated matrix depending on the anisotropy of the material that makes up the beam. So if we had cross anisotropy or other forms of anisotropy in the cross section of the beam, or a heterogeneous beam structure in the cross section, this matrix may well be fully populated. And also I'd like to note the fact that while this constitutive relationship is uncoupled here, this still does not mean that in any given problem we will have an uncoupled axial problem and an uncoupled torsion problem and an uncoupled flexural problem. Through the geometry of the problem and the boundary conditions, all of these problems may well be coupled, even if the coupling does not exist at the constitutive level. Imagine a portal frame. If you apply, for example, a vertical load on a portal frame and a lateral load, the axial shortening of a column is coupled with the rotations and the vertical displacements of a beam that is supported by that column. So the examples are endless. So just remember that this uncoupling at the constitutive level does not necessarily mean that all these three problems are uncoupled. They're indeed coupled for the general case. So let's move on to now we have all the necessary ingredients. Let us now move on to the determination of the element stiffness matrix using the principle of virtual work, in this particular case the principle of virtual displacements, which was expressed compactly as shown in this green box, that the virtual work was always equal to 0 for all possible variations of the generalized coordinates del delta, virtual variations of the generalized coordinates, and the total virtual work was equal to the difference between the external virtual work and the internal virtual work. So if we can compute both of these quantities from the choice of our shape functions consistently, then we are going to, as you will see, end up with a discrete system of equations that will allow us to compute or calculate the delta, the nodal displacements or nodal degrees of freedom. So let's go on computing the internal virtual work. In general, the internal virtual work is as follows, right? Del epsilon transpose times C times E integrated over the entire volume of the member. And recall that epsilon itself was related to the kinematic degrees of freedom through the strain displacement relationships, and the virtual one was, if we use the Galerkin method, using the same shape functions to interpolate the real displacement field and the virtual displacement. So the strain displacement matrix for the virtual field would be identical. And we need to transpose that second expression to exercise it in the expression, the integral on the left-hand side, and that's simply del delta transpose times B transpose. And we can take those two expressions for the real displacement and the virtual resultant strain and the virtual resultant strain vectors and put them in there, and we will get that. And of course, in that integral, both del delta and the delta itself are not functions of the coordinates of the system. They're just generalized coordinates. They're constants with respect to spatial coordinates. So we can pull them outside the integral, and on the inside then we will have an integral that is B transpose CB, and this is our stiffness matrix. So we'll relabel that as simply K, and the nature of the stiffness matrix and its dimensions will depend upon which problem we're solving. Are we solving an axial problem alone? Are we solving a torsion problem alone? Or are we solving a problem that brings in all the ingredients, axial, flexural, torsion? That will depend. That will change the content and the dimensions of the matrices B, C, as well as the vectors delta, and delta. So this is now our internal virtual work. And let's just set that aside and now go about computing the external virtual work. In the external virtual work, we are going to have some discrete agents that will do external virtual work, such as F sub I. So let's assume that these F sub I are forces and torques, all this kind of stuff that do work. And we need to just find their corresponding virtual kinematic quantity, take their products with each other and sum them all up. The right-hand side, the left-hand side and the right-hand side of this last expression is just scalars. And it's going to have a unit of virtual energy, I suppose, virtual work. And we can represent the right-hand side compactly as del delta transpose times F. And the principle of virtual displacements that is shown in the green box up top implies that the internal and the external virtual works must be equal to each other for all possible variations of del delta. And that therefore implies that K times delta must be equal to F at all possible variations. And now, through this principle of virtual displacements, we have taken our ordinary differential equation and converted into now an algebraic equation, which we can solve for delta after applying the proper boundary conditions, because nominally this K that we have devised is going to be singular up to a set of rigid body motions at least. And once the proper boundary conditions are specified, we can then partition and invert this problem to solve for delta as well as unknown reactions on the right-hand side. So we can exercise the generic procedure that we have described above for the axial problem, for example, where if we are just interested in solving trusses and we're interested in the devising the element stiffness matrix for a truss, our B transpose CB matrix would just simply look like that. And if we carry out the integral from 0 to L, which is the volume of that problem, we will end up with this stiffness matrix. And lo and behold, this is identical to what we have obtained before using analytical expressions. And this is not a surprise because in this particular case of the axial problem, we are utilizing shape functions that are exact for the problem at hand. So the stiffness matrix comes out exact and identical to what we had before. In the torsion problem, the case is similar. Our torsional stiffness is just Gj over L times this matrix. And again, that's the same as before. And the why of it is because we are using the exact shape functions for these two problems involving a truss and a shaft that is loaded only at its end, and that is prismatic. If the truss or the shaft is not loaded at its two ends, then, or as you saw before in the example, the cross-section is not prismatic, then these matrices can still be used to obtain a principle of virtual work based solution to the problem at hand, but that solution will only be approximate, not exact. We can also do the same procedure for the flexure problem, say, bending about the z-axis that we kept talking about. Here, our constitutive matrix is just a 1-by-1 matrix EI, and we have all our kinematic degrees of freedom, and our B matrices are the second derivatives of the appropriate shape functions, which are all linear shape functions. And if you carry out the algebra, you're going to end up with a 4-by-4 matrix that correspond to these kinematic degrees of freedom V1, theta Z1, V2, theta Z2 in that particular order. And again, this particular flexural stiffness matrix is identical to what we have obtained before using the analytical solutions. So let us now start combining them. For example, let's just talk about some axial loading and flexure problems. If we are solving a two-dimensional problem of reticulated beams, these two problems will always come together. It will be hand in hand, so we cannot neglect one over the other. We have to consider them together. And so here's our strain displacement relationships, which were the first derivative of the axial displacement field and the second derivative of the transverse displacement field. So now our combo B matrix will be not a 1-by-4 matrix or a 1-by-2 matrix, which was the case for the purely flexural problem and a purely axial problem respectively, but it will now be a 2-by-6 matrix. Our degrees of freedom here are now U1, V1, theta Z1 on the left node, U2, V2, theta Z2 on the right node, and of course the corresponding derivatives that relate them to the internal axial strains, resultants, axial strain and curvature is as follows. So our B matrix is 2-by-6, our delta is 6-by-1. In this particular case, the constitutive relationship is 2-by-2, which in matrix form looks like that. Axial strain resultant times the axial stiffness is equal to the internal axial force F sub x, and the curvature times the bending stiffness is equal to the internal moment M sub z. And then the stiffness matrix becomes B transpose CB with the C shown up top. And if you carry out the algebra and do the integrals from 0 to L, you'll end up with the same identical stiffness matrix we had for this problem. So now let us move on